Hello everyone. So this is going to be a review of some of the types of problems that will appear on your second lab exam, which is going to be on MyOpenMath. So to start, let's say we have an object that's launched, so a projectile launched at some velocity. So I'll draw the velocity vector here. And let's say the magnitude of that velocity is 185 meters per second. So one thing I could ask, and let's say this angle, the launch angle is 60 degrees. So one thing I could ask you is to find the components, right? Find the x and y components of that launch velocity. So to do that, you would project this vector. So you start at the tip, right? Project down onto the x-axis. And then this would be the x component, that would be Vx, and then project onto the y-axis, and then this would be the y component, Vy. And then if we extract the right triangle that contains the reference angle, so this triangle right here, so I'll draw that over here. Then again, we know this angle is 60 degrees. The hypotenuse is the magnitude of the velocity, so that's how fast it was launched at 185, it's meters per second. And then the adjacent side to the angle is our Vx, and the opposite is our Vy. So what trig functions do we need to use to find Vx and Vy? Well, if you remember, right, if we have a particular angle, so in this case it's 60 degrees, the Vx here is adjacent to the angle, and the 185 is a hypotenuse. So what trig function relates adjacent side and the hypotenuse? That's going to be cosine, right? Ca, SOHCAHTOA, so ca. So we know that cosine of 60 degrees should equal Vx divided by 185. And then if I multiply both sides by 185, I can solve for Vx, right? So Vx is going to be 185 times cosine of 60 degrees. And if we work this out, this ends up being 92.5 meters per second. And then to find Vy, well, Vy is opposite the angle, right? It's opposite the 60 degrees. So if I know opposite and hypotenuse, which trig function relates those together? That would be sine, right? So sine of theta is opposite over hypotenuse. So in this case, sine of 60 degrees would be Vy over 185. So now again, if I multiply both sides by 185, I can find that Vy is equal to, so Vy is equal to 185 times sine of 60. And that turns out to be around 160.2 meters per second. Okay, so you'll probably definitely see a problem like that where you have to find the components, right, of that. It's basically just finding the components of a vector. In this case, the vector happens to be the initial launch velocity. All right, another problem that could appear is, let's say you're told the initial launch velocity. So in this case, again, we'll assume it's 60 degrees, the launch angle. And so this is my vector v, it's launched at. And let's say the magnitude is 139 meters per second. So you could be asked to compute the range. So remember, the range is, like, the actual object would do something like this, right? Reach a peak, and then come back down, hit the ground. And remember, the range is the horizontal displacement from the point of projection to a point on the path that's at the same elevation, but if it's launched from the ground, that is the same elevation. So this distance, this horizontal displacement, that would be the range. So the easiest way to calculate this, there's many ways you can do this. Easiest way is if you know the range formula, just to plug into the range formula, right? So we know that R, the range, should be V naught squared. This is really V naught, right? It's the initial launch velocity, times sine of 2 theta divided by g. Well, V naught is given, that's 139. So this is 139 squared times sine theta is 60. 2 times 60 is 120, so this is like of 120 degrees, divided by, and then we want our G to be in SI units, so make sure you use the correct value. This would be 9.8 in this case. And if you work that out, make sure your calculator is in degrees, right? When you plug that in for sine, you're going to get 1,707.4 meters. So that would be the range. 1,007.4. Okay, here's another example. So this is more on Newton's second law. Let's say we have two objects, right? But right on top of one another, so you can, in some ways, you can think of it as a single object. So we have, let's say, a block, call that block 1, and then we have a second block resting on top of it, block 2. And let's say we know the mass of block 1. I'll put it as 40 kilograms. But I'm looking for the mass of block 2. Let's say that's unknown. What else do we know? Let's say we know the applied force, so a force, like someone's pushing this to the right. And let's say there's also friction, so if it's moving, then we'll have a kinetic frictional force acting to the left, so this is Fk, it's a vector. And let's say we're told that the magnitude of that applied force is 400 newtons. And then the magnitude of the kinetic frictional force is 120 newtons. Okay, and let's say we're also told that the acceleration in the x direction is 4 meters per second squared. So using all the information, we want to find m2. So the goal here is to find that second mass. What is the value of that second mass in kilograms? So the way we can solve this is we could use Newton's second law, right? And we can apply it in the x direction. So we have, this is what Newton's second law says, sum of the forces in the x direction is equal to mass. In this case, it really means the total mass, all right, like m total times the acceleration in the x direction. Where we know m total is going to be mass 1 plus mass 2, right? They're moving together. We're assuming 2 isn't slipping relative to 1. It's just moving together. Okay, so what are the sum of the forces in the x? Well, I have Fa acting to the right, so that's plus Fa. I have minus Fk, because it's acting to the left. And that's going to equal m total, but that's going to be m1 plus m2 times ax. So now I can start filling in values, right? Fa is 400. The kinetic frictional force was 120. And that's equal to m1, which was what, 40, plus m2 times ax, which was 4. Okay, and then notice my only unknown is m2, so I can solve this. So first of all, I would subtract on the left-hand side, right? 400 minus 120 is 280. And then probably I would distribute in the 4 here. Probably the easiest way to do it. So 4 times 40 is 160 plus, and then 4 times m2 is 4m2. And then we can subtract 160 from both sides. So I'm going to get 120 is equal to 4 times m2, and then finally divide by 4. Right, so in this case, so this will cancel, right? And then m2 is going to equal 120 divided by 4, which is 30. So 30 kilograms. So that would be my mass of m2. Okay. Here's another question that deals with Newton's second law. Let's say we have an object of mass m. Let's say we're told m, or we're given m is 100 kilograms. Then let's say I have, again, an applied force Fa, just applying to the right. So this is Fa acting to the right. And I have a kinetic frictional force acting to the left, so Fk. Let's say I'm told Fa, and I'll make it 500 newtons. And let's say I'm also told the coefficient of kinetic friction is 0.4. Remember, coefficients of kinetic and static friction are unitless, right? There's no units there, just 0.4, just a number. And we want to find Fk and Ax. So what is Fk? And then what is the acceleration in the x direction? We want to find those two things. Okay, so first thing I would do, remember to find Fk, we can model it, it's equal to mu k times n, right, times the normal force. Well, what is the normal force in this case? Well, if we look at this object, right, there's four forces acting. We have Fa, we have the kinetic frictional force to the left, I have the weight of the object, which is mg acting down, and I have the normal force acting up. So if I just focus on the y direction, right, sum of the forces in the y direction equals may. Well, that's going to be the normal force, which is positive, right? I'm using a coordinate system like this, where this is x and y points upward. So all the normal force vectors in the positive y direction, and then the weight is in the negative y direction, so this is minus mg, and that is equal to 0, because it's not accelerating in the y direction, it's not leaving the surface, so ay is 0. So that means the normal force in this case is just equal to the weight of the object, right? It's mg. So here I can plug in, for normal force here, I can just stick in mg. Okay, so if I plug in my values, right, this is 0.4 times the mass was what? Was 100. And then times 9.8, right, is g. And if you work that out, that turns out to be 392 newtons. So that is my kinetic frictional force acting to the left. That's the magnitude of it. Okay, so now we can apply Newton's second law in the x direction, right? So now I have the sum of the forces in the x direction equals max, because I want to find ax. So what do I have acting in the x direction? Well, I have the applied force, which is positive. I have the frictional force, which is negative, so minus Fk, and that's got to equal max. So now if I plug in, this is going to be 500, right, minus 392 is equal to m, which was 100, times ax. So this is, what, 108 is equal to 100 ax. And then finally, if I divide by 100, then I have my answer, right? That cancels. So ax, the acceleration in this case, is going to be like 1.08 meters per second squared. So that would be the acceleration. So we have the magnitude of the kinetic frictional force, and we found the acceleration. Okay, here's one that's related to what we did in lab. Let's say, I mean, we did all the stuff in lab in terms of the simulations, but this is, we actually collected this data in lab on the air track. In this case, let's say we have a mass of a cart, right? Remember that was like M1. Then we had a pulley, and we had a string going over the pulley. Let me draw that a little better. So pulley, and then a string going over the pulley. And then we have M2, the hanger, right, the suspended mass. And let's say we want to find the acceleration of the system. And then we also want to find the tension in the string. So we want to find A, and then T being the tension in the string. So we derived a formula for A, right? So you can just use that formula. So in this case, A is going to be M2G over M1 plus M2. So in this case, let's say we're told that M1 is 180, so 180, and it was grams, right? We use CGS units in this part of the lab, and then M2 is, say, 20 grams. So if I know that, I just plug in, right? So M2 is 20. You have to be careful, since we're in CGS units, remember G is 980, right? It's not 9.8, it's 980, divided by, and then this is 180 plus 20. If you work that out, you're going to find that this is 98 centimeters per second squared. So that's the acceleration. Now to find the tension, well, we actually derived two formulas. You could either use T is equal to the mass of the cart, M1 times A, or if you want to do it based on the suspended mass, it was T equals M2 times G minus A. Either one will give you the correct answer. The first one's probably a little easier. So if I use T equals M1A, then this is going to be 180 times 98. And that turns out to be 17,640. And remember, the units for force and CGS units are dynes. So that would be in dynes. So this is the acceleration. This is the tension in the string. We just basically plugged into the formulas that we already had derived. Okay, in this example, let's say you're given the mass of the wooden cart. So now this is going to be like a frictional example. So mass of the wooden cart was 0.72 kilograms. And then you're given some information about the force. So remember when I measured Fs max and Fk, I had to look at the graph of force versus time. Let's say that graph looks like this. So this is force in newtons, and this is time in seconds. And let's say the graph looks like this. So it peaks to some value, then it kind of dropped and it plateaued, and then when I stopped pulling, it went down to 0. So what I want you to do in this problem is I want you to find mu s and mu k. Okay, and we know, right, we know that the relationship between the max static frictional force, Fs max, that is equal to mu s times the normal force. So that means mu s is simply going to be Fs max divided by the normal force. And there's a similar equation for kinetic friction, right? Fk is mu k times the normal force. So if I want to find mu k, it'll be Fk divided by the normal force. So the normal force we can figure out, right? We have this object, it's sitting on a flat surface. There's only two forces acting. We have the weight acting down, which is equal to mg, and we have the normal force acting up. Right, they're vectors. So if I apply Newton's second law to the y direction, sum of the forces in the y equals ma(y), then how much, so I basically have the y component of the normal force plus the y component of the weight equals ma(y). But what's the y component of normal force? Well, all of it is acting in the y direction, and it's positive, right? So that's n. And in the weight, all of it's acting in the y direction, but it's negative, so that's minus mg. But the cart is not moving off of the wooden track, right? The horizontal wooden track, so its acceleration is 0. So again, this just tells us in this simple case that the normal force is equal to the weight, right? It's equal to mg. Okay, and that's something we can calculate fairly easily. So the normal force is going to be equal to 0.72, right? That was the mass, times 9.8. So let's say in this case we get 7.056 newtons. Okay. So now, in order to figure out mu s and mu k, we need to know Fs max and Fk. but that we can get from the graph. So when I give you the graph, you're going to have to like estimate what this peak value is. So you kind of go over to the side here and read off this value. Let's say in this case it's around, I don't know, 4.1. And then you have to estimate what this plateau region is. So you kind of go to the side here. Let's say it's 3.6. Okay, so basically what we're saying is Fs max is around 4.1, and here this value is Fk, right? Fk is 3.6. So now I can actually finish the problem, right? Mu s will be Fs max, which is 4.1, divided by the normal force. So that would be, in this case, 0.58. And then mu k will be Fk, which we're estimating is 3.6 from our graph, divided by normal force. And that's going to be around 0.51. Okay, here's another Newton's second law problem involving friction. Let's say we have an object with mass m, and it's moving to the right, but it's slowing down because there's just a frictional force acting on it, right? So it had some initial velocity, and now the only force acting on it is a kinetic frictional force, and it's slowing down. Let's say you're given the mass as 80 kilograms, and let's say you're given the mu k, the coefficient of kinetic friction, is 0.36. So what we want to do is we want to find the acceleration of this object, find ax. So just like before, we have to first calculate the normal force, right? Because the Fk is going to depend on the normal force, but we know that there's two other forces here. We have a weight acting down, which is equal to mg, and we have normal force acting up. So using the same logic as before, right? If I do the sum of the forces in the y direction, that equals may. Well, that's just going to be the normal force acting up minus the weight acting down equals, and it's not moving, this object's not moving in the y direction, that's 0. So the normal force is simply equal to the weight again. Okay, and we can work this out. This is going to be 80 times 9.8. And that turns out to be 784 newtons. Okay, that will allow us to find Fk, right? The magnitude of Fk. Remember, Fk is mu k times n, times the normal force. So this is going to be 0.36 times 784. And that's equal to 282.24 newtons. So now I can apply Newton's second law to the x direction to figure out the acceleration. So I have sum of the forces in the x equals max. Well, the only force acting in the x direction is the kinetic frictional force, right? So this is the only force acting in x direction, and it's acting to the left. It's acting negative, right? We're assuming our coordinate system is like this. X is positive to the right, y is positive vertically. So it's acting to the negative x. So this is going to be negative Fk equals max. So you can either solve now for ax or you can plug things in. Let's just plug things in. So this is going to be negative 282.24 is equal to 80 times ax. And then finally, if I divide both sides by 80, right, that cancels. I'm going to get my acceleration, and it should be negative, which makes sense. Negative, in this case, it's going to be 3.53 meters per second squared. So that would be the acceleration of that object. Okay, next, let's, there definitely will be some stuff on torques and rotational equilibrium. That's very important. So let's do some problems on that. Let's say I have a seesaw, so like some board, and let's say the axis of rotation, like the knife edge and the axis of rotation are right in the center, and I have a mass 1 here. Let's say its distance is 0.1 0.5 meters away. And then let's say I have M2 sitting here. Let's say it's 1 meter away from the point of rotation. And then I have M3 on the other side. And let's say this distance is 1.5 meters. Okay, and let's say we're given M1 is 10 kilograms. Let's say we're given M2 is 20 kilograms. And we're looking for M3. So we want to solve for M3. That's unknown. Okay, so first of all, what are all the forces acting on this? Well, I have, let me draw this again here. Assuming like the seesaw itself, that board is uniformly distributed, the weight of the board is going to act straight down at the center, right? And we're assuming this is at the center of mass of the board. So this is like the weight of the board. Then I have a normal force acting up, right? That's from the stand itself, from the knife edge there. Then I have a weight due to object 1. I'll call this weight 1. And we know how to compute that, right? It's going to be M1G. And then I have weight due to object 2. So weight 2 is M2G. And then the weight due to object 3, that's going to be M3G. We're assuming it's in rotational equilibrium, right? So it's balanced, right? Wherever we place those three masses, it balances. So now what I can say, since it's in rotational equilibrium, I can say that the sum of the torques about any point I choose, and I'm going to choose to analyze it about this point right in the center here, the sum of the torques has to equal 0. So I have 5 forces, I'm going to have 5 torques, right? So I have a torque due to weight 1, plus a torque due to weight 2, plus a torque due to weight 3, plus a torque due to the weight of the meter stick, plus a torque due to normal force. That's got to equal 0. But because the normal force and the weight of the stick, of the board, is passing right through the axis of rotation, right? The line of action goes right through the axis of rotation. There's no moment arms, so these two are going to be 0. They're not going to contribute any torque about that point. Remember, torque, to find it, it's plus or minus the force times the moment arm. And they have no moment arm. Okay, so then, but I do have 3 other torques, right? So torque due to weight 1. Well, weight 1, remember that's this one right here. So the force is the weight. So it's going to be mg, right? M1g. So M1 is 10 times 9.8. That's the force. Now I need the L, right? I need that moment arm. Well, remember, the moment arm is the perpendicular distance from the line of action of the force. This is the line of action of the force. So the perpendicular distance is simply going to be this horizontal distance here, right? And that was 0.5 meters. So the moment arm for M1 is 0.5. And then, since if that was the only force acting, it would tend to rotate the board counterclockwise, right, about the point of rotation. This is a positive torque. Okay, then I do weight 2. So weight 2 is, well, the weight is going to be 20 times 9.8. The moment arm is simply going to be this distance, but that's 1 meter. So that's 1. And that torque is also positive because it would cause a counterclockwise rotation. And finally, on the other side, I have weight 3. So the torque due to weight 3 is going to be the force, which is the weight. I don't know M3, so I'll leave it as M3 times 9.8, and then times the moment arm, which is this distance, right? And that was 1.5. Remember, up here we labeled it as 1.5. So this is 1.5. But since that force would tend to rotate the board clockwise, this is a negative torque. And then that's got to all equal to 0. So notice that my only unknown is M3. I can solve this for M3. In fact, if I bring this term, or if I add this term to both sides, I'll bring it to this side, then I'll divide by these two values. So basically you're going to get this. You're going to get M3 is going to be this whole thing divided by 9.8 times 1.5. And if you work that out, you're going to find that it's 16.7 kilograms. Okay, so you could definitely get a problem like that where the object is in rotational equilibrium and you have to find the sum of the torques, right, to figure out the answer. Okay, here's another one. Let's say I have a meter stick and we're told that the knife edge, so this is the center of mass, let's say of the meter stick, let's say it's right at 50 centimeters, so right in the center, and then the knife edge is at 25, so this is what we're going to consider our axis of rotation to be, so this is at 25, and let's say we have a weight acting at 3 centimeters. So this is like W1, right? This would be the normal force pushing up, and then we have the weight of the meter stick that acts at its center of mass, so that is like W. So let's say we're given W1, the magnitude of this weight. These are really vectors. Let's say you're given the magnitude of W1 is equal to 1.72 newtons. And we want to find the weight of the meter stick, which is W. Okay, so we want to find W given W1 and given those measurements. Okay, so first thing I would do, let's figure out the moment arms, right? And we're assuming this is in rotational equilibrium. You place these in those locations and the whole thing is balanced, right? It's not rotating. So to figure out the moment arms, well, this is the line of action of W1. So the moment arm is the perpendicular distance from the line of action of the force to the axis of rotation. So again, it's just going to be this nice, easy horizontal distance. And we can get that by subtracting, right? 25 minus 3, and then making sure we convert it to meters. So if you do that, this is going to be 0.22 meters. And then the moment arm for W will be this distance, right? That's the perpendicular distance. And that would be 50 minus 25, which is 25 centimeters, which in terms of meters is 0.25 meters. Okay, so now we can do sum of the torques equals 0. So I have a torque due to W1 plus a torque due to W, the weight of the meter stick, plus a torque due to the normal force, that equals 0. And since the normal force passes right through the axis of rotation, it doesn't contribute a torque. So that one's 0 off the bat. So what is the torque due to W1? Well, here, so now I have to be a little careful, right? I don't need to multiply by G anymore because now, right, remember torque is always plus or minus force times moment arm. And normally I know the mass and I have to multiply by G to get the weight, which is the force. Here I'm already given the weight. So the weight is the force. So this is going to be 1.72, right, times the moment arm, 0.22. And since W1 would tend to rotate it counterclockwise, that one's positive, then the torque due to W is going to be W, which I don't know, times the moment arm, 0.25, and that torque is negative, and that equals 0. So notice I didn't have to multiply by 9.8 because I already have the weight. I already have the force, which is the weight. Normally we're just given the mass and you have to convert into weight. Here we already have the weight itself. And then you can solve this, right? So if you solve this, you're going to find that W is 1.72 times 0.22 divided by 0.25, right? And that ends up being around 1.51 newtons. So that would be the weight of the meter stick. Okay, we talked about like the biceps force, so I could give you a problem like that. Okay, so let's look at one problem with like the biceps. Let's say we have, I'll draw, this is my forearm and hand. I have the upper arm, right? So this would be like the elbow joint, and that's where we're going to consider the axis of rotation to be. And then I have a muscle force in this direction. And then I have the weight of the forearm and hand acting at the center of mass. And then the weight of the object acting at the end here. And then I need to know the moment arms. Remember, this is like the moment arm of the form and hand, which I call D. So instead of L, I called it D, so I'll call it D in this as well. So D form and hand. Then this would be like D of the object. And then this distance in here would be like D for the muscle. Let's say you're given a bunch of information. Let's say you're given D of the muscle is 0.045 meters. And then D of the form and hand is 0.18 meters. And then D of the object is, say, 0.31 meters. I would have to give you enough information to find the weight of the form and hand, right? So if it's like cadaver data, if you knew the total weight of the person and you know that the weight of the form and hand is a certain percentage, you could easily calculate it. So let's say you do that and you get like 18.8. This will be very similar to how we did it in lab. And then let's say the weight of the object is 20 newtons. So we want to calculate FM, right, the muscle force. So really, if you have all that information, all you have to do is plug into the formula that we derived. Remember, the muscle force is going to be the weight of the form and hand. This comes from torques, right? Times the moment arm of the form and hand, plus the weight of the object, times the moment arm of the object, divided by the moment arm of the muscle. So in this case, it would be equal to 18.8 times 0.18 plus 20 times 0.31, all divided by 0.045. And if you work that out, it turns out it's like 212.98 newtons. And then, just like in lab, I might ask you to find the ratio of the muscle force to the weight of the object, right? So that means just find the fraction, Fm divided by weight of the object. So in this case, it'd be 212.98 newtons divided by, what did I use? I think it was 20, right, is the weight of the object. And if you do that ratio, you're going to find it's like 10.65, which meant that the muscle force was 10.65 times as large as the weight of the object. Okay, so it'll be very similar to what we did in lab. I could also give you a question like with finding the center of mass of the human body. Right, we have to find Z and Z as a percentage of height. But again, you're just going to plug in. So if you're given a bunch of data, remember this is the formula. Z is equal to the force that the scale reads when the student is lying down on the board minus the weight of the board, that would have to be given, divided by 2, times the length of the board, L, all divided by the weight of the person. And that gives Z in inches. So this is like the height of the center of mass of the person from the floor. And it was in inches in this case. And then I might ask you to calculate Z as a percentage of their height. So then you would have to do Z divided by the person's height times 100. And that's basically Z as a percentage of the height. Okay, so definitely probably be a problem like that, but that's plug and chug. Okay, let me do one more. So another possibility that could come up. And there could be other questions as well, but this is like, I'm highlighting like the main types of problems that will be on the exam. Let's say we have this. Let's say we did this one in lab as well. Let's say we have a stand with a beam, a wooden beam, right? This is going to be the axis of rotation right here. And let's say we have the weight of the beam is acting at the center. That's really a vector. And then the weight of a hanger, an object, is at the end. I'll call it weight of the hanger. I think I called it in lab. And then we have a tension in a string which connects up here. That goes something like this. This distance from here to here, this was 30 centimeters, but we want to do that in meters, so it's 0.3 meters. This distance from here to here, where this attaches, where the string attaches, that's going to be 40 centimeters, which is 0.4 meters. This distance was 46 centimeters, but that's 0.46 meters. And then if I go all the way from here to here, and this was 60 centimeters, which is 0.6 meters. So if this whole thing is in rotational equilibrium, we want to calculate T, right? So let's say we're given a couple of things. Let's say we're given the mass of the beam, which I'm calling MB. Let's say that is equal to 285 grams. So immediately you want to convert that to kilograms. It would be 0.285 kilograms. Then say mass of the hanger, which I'm just going to say is MH. Let's say that is 365 grams. So that's going to be 0.365 kilograms. And given all the information, we want to find T, the tension T. So just like in lab, the first thing I would do is find this angle, right? Find the angle that the tension, the string makes with the horizontal, with the beam itself. So to do that, you can kind of extract out this right triangle here. So remember, this was 0.40 meters. This is 0.46 meters. And we want to find theta. Well, relative to the angle theta, right, we know the adjacent side, we know the opposite side. So I could use tangent, right, to figure out the angle. In fact, I know that tangent of theta must equal the length of the opposite, 0.46, over the length of the adjacent, 0.40. So then if I want to find theta by itself, I have to take the inverse tangent of both sides. Well, inverse tangent of tan of theta is just theta, right? That's why we get theta on the left-hand side. And in the right-hand side, you have to do this in your calculator. And you're going to find it's very, very close to 49. We're going to call it 49 degrees. Okay, so that's going to be useful. Why? Because ultimately, I want to find all the moment arms. Well, for the two weights here, these are easy, right? Because, again, if this is the line of action of the weight of the beam acting straight down, this is our rotation point here. By the way, there is another force here, like a force, the joint force, but we're not going to have to worry about it because it passes right through the axis of rotation, right? We're not going to worry about the torque due to it. So if I look at the weight of the beam, right, that line of action is straight down. So that means the moment arm for the beam is just this distance, this perpendicular distance, but that's 0.3 meters. So that's easy to find the moment arm of the weight of the beam. And in the weight of the hanger, it's going to be this distance, which is 0.6. The hard one is finding the moment arm for the tension, right? So in this case, we want the perpendicular distance, which would be this distance, right? That's perpendicular. So that would be like L. So in this case, if I draw it down here, it's this distance that we want to find, the one that's perpendicular L. So what we can do is I can draw this triangle over again. So it looks like this. I'll do it over here. And I know several things, right? I know that this is 49 degrees. I know the length of the hypotenuse because that was 0.4 meters, right? That was 40 centimeters, 0.4 meters, and I'm looking for L here. So now, relative to the angle, I have remember, be careful, this is not this is not adjacent, right? This is adjacent. This is a hypotenuse because it's along its side. So I have opposite and I have hypotenuse relative to the angle. So what trig function relates opposite and hypotenuse? That's sine. So I know that sine of 49 degrees is equal to L over 0.4. So that means L is going to be 0.4 times sine of 49 degrees. And that ends up being around 0.302 meters. Okay, now that I have all these things, I know that this beam is in rotational equilibrium, so now I can apply the sum of the torques. Right, so now I can use the fact that the sum of the torques about our axis of rotation has to equal 0. So I have several forces, right? I have a torque due to the tension, plus a torque due to the weight of the beam, plus a torque due to the weight of the hanger, plus a torque due to the joint force. That's equal to 0. And we already know that this one is 0 because it goes right through, passes right through the axis of rotation, right? So there's no moment arm there, so it's not going to contribute a torque. All these will contribute a torque, but not that one. Okay, so what does the torque do to the tension? Well, it's going to be the force, which is the tension, that's unknown, times the moment arm, we just figured that out, the L, it's 0.302. And if you think about it, that tension will cause the object to rotate counterclockwise, right? So it's a positive torque. Then I have torque due to the weight of the board. Well, the weight of the board is going to be, the force is the weight, right? Which is the mass. So that was 0.285 times 9.8. That's the weight of the board. And then what was the moment arm? Remember, it was only it was 0.3 meters, right? 30 centimeters or 0.3 meters. And that torque would be negative because it would tend to rotate it clockwise. And then the weight of the hanger, so this is H here, is going to be the mass of the hanger times 9.8, right? That's the force, the weight. And then the moment arm was 0.6 meters. And then that torque was also negative, right? Remember, if you imagine that this is the only force acting, right, how would it rotate the beam about this point? It would rotate it clockwise. And same thing here, clockwise. The tension is counterclockwise. So tension's positive, the other ones are negative. And this has got to equal 0. And notice here, I can solve this for t, right? If I bring these two terms to the right-hand side by adding to both sides, then basically you're going to find that t, tension, is equal to this whole thing on the right-hand side divided by, and then I can divide by 0.302. And if you do that, you're going to find that the tension in this case is equal to 9.88 newtons. Okay, so very similar to what we did in lab, we will get a problem very similar to that or you guys will get a problem very similar to that on the second lab exam. Okay, hopefully that was helpful. If you can come to class the last 2 weeks, I will be doing a review like this. If not, then you have this video to watch at least. Great, thank you.